so we have a water skier who's jumping up in the air. Okay, now one of the things it says is the skier lets go of the rope. Okay, let's go of the rope when he leaves the end of the jump ramp. Why does it have? Why does the problem have to have let go of the rope? Exactly, the rope would keep pulling him. All right, so it would be a force exerted on the system from the outside. Wouldn't be in isolation, so energy would not be conserved. Okay, so in order to conserve energy, that has to be the case. All right, so here we see we got some height here. We're trying to calculate that. This is what kind of problem? How would you characterize this problem? I already sort of gave you a clue, but how would you characterize it? What did you say? Conservation of mechanical energy. Yes. Is he a projectile? Yes, he's a projectile for our purposes. Okay? But instead of solving it with dynamics and kinematics, projectile motion stuff, all we're trying to solve for is this height right here. We don't have to worry about it as a projectile. All we have to do is think about the energy before and the energy after. When I say the energy before, what do I mean? What I'm saying is, what is his total energy right here as he leaves the ramp? And what is his total? Like, compare that, just for me, right now, compare that to his energy right there at the green point. How do those energies compare? Yeah, they're the same. They have to be, okay? So actually, technically, what do we have to do? We should talk about his center of mass, but that's no big deal. Okay, so what is the height? That is going to be the change. The change in height is going to be going to determine his what? Change in what? How are we going to figure out his change in potential energy? Okay, well, what do we know the change in? We know the change in velocity. Yep, I heard that. So if we know the change in velocity, what do we know? What other change do we know? We're thinking energy. What energy is associated with velocity? Kinetic energy. Okay, so we know his change in kinetic energy. Since we know the total's the same, that way we'll be able to figure out his change in what? Potential energy. Right, if we know the change in potential energy, we can figure out the height, because we know what G is, and if you have done enough of these, you'll recognize the fact that mass is going to cancel out. Notice it wasn't given. So maybe you said, oh no, I can't calculate his mass, but that's all right. We can figure out because we can cancel it out as we go across. All right, so right here, we have, at the beginning, we have his kinetic energy and we have potential energy. All right, so potential energy, mgh, plus kinetic energy, 1/2 mv naught squared, has got to be equal to his total energy up in the air, right? This is his energy budget right here that we just wrote down. So then we have mg H final, I should make this H naught here, okay? Plus 1/2 mv squared at the top. All right, so anything that we can get rid of here, anything we can do to simplify things to start with. M's cancel out, and it's a little bit tricky because it shows him up in the air, but what are we allowed to do? What are we allowed to do when we're defining 0? We could just call it 0. We could call it whatever we want. We could put this in as some value. We could put this H naught in as some value, and this would be whatever that is plus whatever it is, but it would just subtract that anyway. Okay? So we'll just call this 0. And then his final height is just the delta H. Does that make sense? All right. So now just all we have to do is rearrange and do some fun algebra stuff. So we're going to say that H is equal to 1/2. We already got rid of the M's. In fact, let's do it so I don't forget it. All right, so we got 1/2 v squared minus v naught squared. Okay, wait, let's see. We are keeping this. So this is actually backwards, right? If we're keeping this and we're subtracting this by putting it over here, right? And then I just flip those over. So we got 1/2 v naught squared minus v squared over what? Over g. That's all we got to do. All right, so now the calculator brigade is out there, and they're going to help me here. We got 1/2, well, we could just say over 2g, right? We could say v naught squared. V naught was 14 meters per second. squared minus 13 meters per second squared over 2 times 9.8 meters per second squared. So now we got all these units in here. What do you think we ought to do? Dimensional analysis. All right, so we got meters is going to cancel out one of these meters. All right, second squared goes away, and that gets rid of that and that and that and that, so we just got meters on the top. Okay, because this one went away because of the square from the top. Okay, so 196 minus 169. Oh, by the way, I want to show you guys a trick. I'm sorry. Never mind. I'll show you the trick later. All right, so 14, just what do we got here? 1 point what? 1.4 meters. It's like 1.38, 3.37. 1.4 meters. All right, that's the answer.